Welcome to our 2012 Bottle Rocket project. My name is Ritik Gangopadhyay,
I'm Yoon Yang.
and let's get started. So let's start with a brief introduction overview of what the project is. We are using ODE45, a MATLAB numerical integrator, to solve for the trajectory and flight of our model bottle rocket. So the bottle rocket is a very simple system. It's essentially a 2-liter bottle that is filled with water, and this is set up on a launch stand such that when the launch stand rods are unlocked, the rocket is going to launch off the stands and produce a large amount of thrust, and that's going to give us a nice bottle rocket trajectory.
And we use 3 approaches to solve our trajectory. The first is a 10-step problem-solving method, and the second is a numerical integration of ODEs, and the third is utilizing the aerodynamic principles and their equations. And so we have 3 phases in our one trajectory, and phase 1 is the water expulsion, and the second phase is when the water is expelled and the air pressure inside of the bottle equalizes to the ambient pressure. And the third is our ballistic phase, is when the forced thrust equals 0, and we set up another ground state when the bottle rocket hits the ground and the ODE stops calculating.
So let's just talk a little bit about ODE45. It's essentially going to go through our 7 selected state variables, which are the position X, position Z, velocity X, velocity Z, the mass of the air, the mass of the water, and then volume of air inside the bottle. So we're going to be able to get those 7 state variables at each specific time, and ODE is going to basically put those together in vectors, and then we're going to be able to plot our trajectory with the ODE45 results.
This is our verification plot. This came from part 1 of our project, and this is what we use to make sure that our trajectory for this assignment is working.
So after that, we plotted our time versus thrust, and this time versus thrust is gathered from our final results, which we will talk about in a couple slides. So essentially, we are expecting a large amount of thrust at the beginning of the flight, when the water is just coming out of the rocket, and then as the time increases, the thrust is obviously going to decrease because eventually the rocket's going to hit the ground. But right around here at this 0.25 second mark, that's when we're going to see a discontinuity, because ODE45 doesn't 100% accurately get everything within your time ranges at every specific time. And so then we're going to see a little discontinuity, but it should be a sharp dip, which is what we see here. And this is indicative of the phase 1 to phase 2 transfer. So then after that, we expect our thrust to go to 0 during the ballistic phase, and then it'll hit the ground. So this all makes sense to us.
This is when we vary our parameters. That this is a result, trajectory result. So as you can see, if we increase the pressure of the air, then we will have a much further and higher trajectory. And when we have a lower pressure of air, then we'll have a much lower and the shorter trajectory.
Yep, and so when we vary the volume of the water, we're going to see one weird result here. So that's when there's no water, we're going to still get a nice trajectory here, because that makes sense because the air is still pressurized inside the bottle, so we should still get a result. And as you increase water in the bottle, that's going to make sense because you're going to have more of that thrust coming out of your bottle to give you a better trajectory.
Okay, this also makes sense. This is a varying coefficient of drag. When we have a low drag, then we're going to have a much higher trajectory, much higher flight. And when we have a higher coefficient of drag, then we'll have a much lower and shorter flight.
So this is our launch angle variation. So obviously this makes sense as a result, because if we have low launch angle, you're going to go far but not high, and then if you have a high launch angle, you're going to go high but not, you're not going to cover any ground. So this result makes sense as well. So then pretty much when we put together all these variations, we said, okay, coefficient of drag at 0.2 is already very close to the results we wanted with the initial conditions and parameters. So we just decided to vary the gauge pressure with this coefficient of drag 0.2, because gauge pressure is the second leading factor we found. And so we kept the launch angle of volume of water the same as the initial conditions to reach our distance of flight of 85 meters. And then this red here is very hard to see, but it is the phase 1, the blue is phase 2, and the green is phase 3. And these are comparing these to other people's plots. And just from a general sense, using steps 9 and 10 of the problem solving method, we see that these results are accurate and sensible to other results.
Okay, so to conclude, we use numerical integration and system of ODE to find our trajectory of our racket. We were able to plot our trajectory using ODE 45 to solve our differential equation. Once we calculated our trajectory, we were able to determine the flight parameter that will allow bottle rocket to land within the 1 meter of the 85-meter target. And so, yeah, this concludes our findings and our results. And this is our reference, and thank you for watching our presentation.
Thank you.